All right, our first example of working with partial fraction decomposition is this guy. We have x plus 7 divided by x squared minus x minus 2. That's the antiderivative with respect to x. And to really understand what's happening here, I want to take just a quick look back at some of your glory days in basic algebra. So somewhere back in the past, you had some sort of maybe a high school or a basic algebra somewhere where you talked about adding these rational expressions. And recall, when you add these, if you have two expressions like this, you need to get a common denominator. This is just a stroll down memory lane here. Or maybe it's a drag down memory back alley. And so you adjust the numerator, so this becomes x minus 1, and this becomes 3 times x plus 4. And when you add those, you get 2x plus 3x. What is that? That's 5x. And then when you get negative 2 and plus 12, negative 2 and plus 12 is 10. And then this multiplies out to be x squared plus 3x minus 4. Okay, so this particular, I just made this up out of whole cloth. This is just some example I picked out of the sky. But the point is this. You learned back in basic algebra to take two fractions being added or subtracted and combine them into one larger fraction. Well, look, what we have here is exactly this structure. Our task is to take this expression and work backwards to find the two fractions that came up. These are called the partial fractions. That's where this name comes from. So these are called the partial fractions of this rational expression. And so our task is this: take this form, convert back to here, or more to the point, take this form, convert back to it. So the antiderivative of this expression is going to be the antiderivative of, now what's it going to look like? It's going to look like, here we have x plus 4x minus 1. Notice those are the factors. So there's going to be, when we factor this, let's first get this expression factored. So this is x plus 7. And then this factors into x minus 2, x plus 1. Again, the order doesn't matter. I'm just going to put the x minus 2 first. But the point is this. See how each of these factors becomes the denominator of one of these fractions. So each of these denominators, each of these factors becomes the denominator for the two fractions. So there's going to be an x minus 2, and there's going to be an x plus 1. Now the key is this. Here you were given the numerators, and you worked this direction to find this larger polynomial. Now we have this polynomial. Our task is to work backwards to find out these two numerators. And that's the whole procedure of partial fractions, is finding these numerators. More to the point, finding those coefficients. Now typically we denote them A and B, and if you have three fractions, A, B, C. If you have four fractions, A, B, C, D. I'm going to denote them with capital letters. It's a pretty common practice, and so that's what I'm going to work with. And so the point is this: if we can take this expression and do this procedure we're going to talk about and rewrite it in this form, then we've seen from our previous review, this is a natural log form, this is a natural log form. So not only can you do this antiderivative, you can do it very easily. All we need to do is find these coefficients, these constant multipliers, these numerators. So these are called the partial fraction coefficients. And as soon as we find those, then we're essentially over. So that's the procedure. It's algebraic in nature. It's just a deep, deep cut into your glory days in basic algebra. And so that's what I'm going to write here. So let's start the process from scratch. All right, so factor the denominator. I need an integral sign. This is x plus 7. And then this is x minus 2, x plus 1. It doesn't matter what order you place them in. It's irrelevant. And what we're going to do is this. We're going to take just this piece. Forget the antiderivative, forget the differential. Just take this expression, simplify it, and then take that and put it back in the integral. We're going to define what to substitute into that red box. So here's the procedure. Write this expression. And Each denominator, as we saw, each denominator gets its own individual partial fraction. If there were multiple factors, you would have multiple fractions. Each denominator gets its own individual little partial fraction. The numerators are what we're looking for. So this is don't know yet, and this is don't know that yet either. And now everything here is just 100% basic algebra. What we're going to do is this. Clear the fractions. That is to say, multiply both sides of this equation by that denominator. Multiply both sides of the equation by that denominator. And even though it's a denominator, you multiply it as a numerator. Even though it's a denominator, you multiply it as a numerator. And so whatever you do to one side of the equation, do the same to the other. Multiply everything through. So you get multiplied by this denominator, you get multiplied by the denominator, all God's children get multiplied by the denominator. Now what happens here, on the left-hand side, it is particularly easy. It's very straightforward on the left-hand side because here, when you multiply this in, is it clear? This x minus 2 cancels with this x minus 2. When you multiply in, this x plus 1 cancels with this x plus 1. And so these two factors cancel with those two factors. And all you're left with on this left-hand side is this original numerator. That will always be the case. It's always going to flow down that same familiar path. Now, in this scenario, here, this gets multiplied by the first term. It gets multiplied by the second term. Do you see what happens? Now, I'll just write this in some purple. Don't write this what I'm doing here in purple. This would be a times, that would be times each of those two pieces, x minus 2, x plus 1. But you see the x minus 2 is in denominator. And so that falls out, and all you're left with, do you see what you're left with? You're left with a times, because here, this x minus 2 cancels with that x minus 2, the a remains, and the x plus 1 remains, and just leave it like that. You'll see why here in just a bit. Same song, third stanza. Multiply in, multiply in, multiply in. In this case, the x plus 1 cancels with the x plus 1. And we have b times the x minus 2. And we have this. This is called, if you want to, if you're ever on Jeopardy sometime, this is called the basic equation. It turns out the basic equation, once we find a and b, as soon as we find a and b, the basic equation is true. This is a true statement for every possible choice of x. You can choose x to be anything in the world you want, plug that value into here, and this will be a true expression once we find a and b. If you want x to equal 15, pick x to equal 15. If you want x to equal 197, plug 197 in, that'll be a true statement. If you want x to equal negative pi, that will work. Any value you like. Since all of them work, what we're going to do is choose the appropriate x value to make this work the way we want it. And those x values that you choose an x value that causes that to become 0. Choose an x value that causes x minus 2 to become 0. Is it clear? We choose x to be 2. So what I'm going to do up here, I'm going to say let x equal 2. Plug x equal 2 into all this expression, and that's going to allow you to find one of the coefficients. On the left-hand side, 2 plus 7. On the left-hand side, this implies we have 9. On the right-hand side, if x is 2, this is a times 3. But look, if x is 2, this vanishes. That's the reason you choose 2. You can choose any number you want, but use the one that's going to do what you want it to do. That vanishes. And if that vanishes, we can solve that. And we know one of our coefficients now. All right? The next piece is same process, different number. Now we can go back and we can choose x to be anything we want to choose. Choose x to make this expression equal to 0. If I choose x to be negative 1, do you see negative 1? Negative 1 causes that to become 0. So if I choose x equal negative 1, that's the point. You choose x to make these factors on the right-hand side vanish. If x is negative 1, we have negative 1 plus 7, that's equal to 6. If x is negative 1, that's 0, this vanishes. And we have b, negative 1 minus 2 is negative 3. And from that, we have b is negative 2. And we have the values that we need. I'm going to erase this expression here. In the future, very often, I won't write this on the right-hand side. I'm going to conceptualize this. I'll write it on the left, distribute here, distribute here, distribute here. So I'm going to conceptualize that, and that'll be fine. It'll save a little space and save a little writing on your part, too. All right, so we have a is 3, b is negative 2. Replace this expression with its partial fraction equivalent. So the integral becomes, we have a, which is 3 over x minus 2, and plus b is negative 2. My recommendation, write this as plus negative 2. Try to not do, be very careful. You may write this as negative 2 over. There's a place later on where that becomes, there's a negative sign you might drop. My recommendation is just leave this as plus negative 2 over, what was it over? It was over s plus 1. And then, look, what I have here is not correct. This is not correct. This is not correct. If you have multiple terms, these need to be grouped together. If you have multiple terms, the integral must be grouped. Now, the rest of this is straightforward, because now, once we have the partial fractions, we can do the antiderivative. Constant multiplier multiplies along. This is the natural log form. And then constant multiplier multiplies along. This is also the natural log form, and we're out. All of this algebra is the whole point of that is to get your ducks in a row so that the antiderivative becomes very easy to do, or something that you can handle. So you change this expression into the partial fraction decomposition. The antiderivative of the original is equal to the antiderivative of the partial fractions. And in this case, that's very straightforward because that's just the natural log form. Typically, in category 1, this is the simplest of the 4 cases. In category 1, typically, you're going to be using the natural log form almost exclusively. So we're going to practice this a little bit, and then that should not be too much of a hassle.